All right, so tonight we're going to carry on with our discussion about derivatives, which of course is probably the most important chapter that we're going to cover because, or except maybe for integration, but we left off last time after we finished up with the product rule and the quotient rule. We saved for today the idea of what's called implicit differentiation. So this is a technique that's used when we have functions that are, let's just say, very, very complicated. And first, they're going to tell us the difference between what are called implicit and explicit functions. So the idea here is that if you have a function, and let's say something like this. Oh, I don't know. It could be anything. Y equals f of x equals 3x squared plus 7. Okay, a parabola. So this is an explicit function because it's written out as y is a function of x. Okay, so now up to this point, I mean, really, this is the only kind of function you've ever encountered. So what else, how else could a function be expressed? Well, how about this? Xy equals 1. Well, that's different because right now, the way it's written, we don't have y written as a function of x, although we can rearrange it to get it into that form. But when it's written like this, we say that this is an implicit function. Because, in other words, the relationship between x and y is implied by this equation that we have here. And so it'll turn out that sometimes it's not actually possible to separate out the x's and the y's and create an explicit function. And if that's the case, then we have to use some different techniques for solving for the derivative of y with respect to x. So in other words, what we're about to do is really meant for cases where the function is so complicated that we can't realistically strip apart the x and the y terms and then have an explicit function y in terms of x. So like here's one. How about if you had x squared? This doesn't look promising. Let's see. Uh-oh, now what do we do? We've got x squared minus 2y cubed plus 4y equals 2. Well, even here, you could actually rearrange it, but it's going to be very difficult because of the high exponents on the y's. Yeah, you can see it's going to be a bit of a mess. It's probably not worth our while to change it algebraically. If we need to know the derivative of dy dx or f prime of x, this is a case where it probably would be quicker and easier to simply use what's called implicit differentiation. So how does that work? Well, in a lot of ways, it's really no different than what we're used to seeing, except, well, you'll see how it's different. So keep in mind that throughout this whole process, we are still differentiating y with respect to x, okay? We're still assuming that y is a function of x, and so we're looking for the derivative of y with respect to x. But for some terms in our expression, the normal rules will be a little bit different, okay? So in other words, when we have terms that are only either constants or functions of x, we use the rules that we're used to seeing. When we have a y term, we have to use the chain rule, okay? And we're going to use it in a somewhat different way than what we're used to seeing. Now here we have no problem. I mean, clearly the derivative of x cubed with respect to x is 3x squared. We know that from the power rule. Fine. So in other words, because this is a this expression is written in terms of x only, we can use our normal rules of differentiation. But what about this case? Now we're getting into some unique territory. And so here's how it works. And they're trying to help us remember what we're doing here, because if you notice, we're taking the derivative of y cubed with respect to x. And as they point out here in blue, the two variables disagree with each other, and that's how we know that we have to use the chain rule. And so because y is itself is a function of x, there's an implicit chain rule going on here. And so here's how this works. The derivative of y cubed. Now, by the way, let's just remind ourselves, if we were taking the derivative of x cubed, we would get 3x squared. So in that sense, nothing's really changed, because the derivative of y cubed with respect to x will include the term 3y squared. But then, in order to apply the chain rule, we're going to end up with dy dx. Okay, so that's a consequence of the chain rule. Now, by the way, in some books, and possibly this book too, it depends on notation is, we've got a lot of different notations that mean the same thing. I just want to remind you quickly that f prime of x is the same thing as dy dx, and sometimes this is written as y prime. So you might see in some books the dy dx is written as y prime. Just be aware, if you do see that, it is the same thing. All right, but anyway, so this is the part that's new. The fact that we have to use the chain rule because we're differentiating y here. And so we do need to apply the chain rule, which means that whatever we get here using the power rule, we also need the dy dx. Okay, let's see what other examples they have. Oh, okay, so here's another one. This is a good one. So you've got 3x, x plus 3y. So when you differentiate this, as always, you can break it up into two parts. And then treat them each separately. And so we're going to do that right now. Wait, let me just do one thing before I forget. All right, so the first term, it's easy. We know how to do this. The derivative of x with respect to x is simply 1. Now for the second term, though, we can rewrite this as 3 dy dx of y. And so when we're using implicit differentiation like this, the derivative of y is simply either dy dx or y prime. Okay, so let's go through that again. So then we bring them together. As you can see, they've done up here. And so we end up with 1, which is the derivative of x with respect to x. And then 3 dy dx is the derivative of 3y. And again, because we're differentiating y, that means we must use the chain rule, and we still need at the end there that dy dx. So yeah, this is definitely going to take some getting used to. Now, oh my God, look at this one. All right, here we go. We have our old friend, the product rule. Well, of course, we just learned about it. So it's actually our new friend, isn't it? So remember how that works? Whoops. Okay. So in other words, it's when you have a product like this, you're actually taking when you apply the product rule, you end up with the first function times the derivative of the second plus the second times the derivative of the first. So the same thing will be true here. So they're writing it as d. So if you think of this as, let's say, f of x, so then we don't want to use the same notation because, well, all right, we'll just leave it the way it is and follow along with their notation. So the first term is x. So we just write x. Then we need the derivative of the second term, which is y squared. And remember, based on what we were just doing, that's going to be 2y based on the power rule, but then we apply the chain rule and we have dy dx. Okay. Then we have the second term, the y squared, times the derivative of the first term, which is simply 1. All right. So we end up with ooh, boy, that was pretty complicated. So 2xy dy dx plus y squared. Okay, so in other words, it's still the product rule, but applied in a somewhat different way. So, this is one of those cases where, we're going to need some practice. So, let's see. So here's the general rules. Differentiate each side with respect to x, collect all terms involving dy dx on the left-hand side, and move all the other terms to the right-hand side. Factor out dy dx on the left side of the equation and solve for dy dx. Okay. So here we go. We have y cubed plus y squared minus 5y minus x squared equals -4. So imagine trying to split that up into y's on one side and x's on the other. Well, I mean, it's not going to work, okay? Because you ultimately would need y equals some function of x, and that's not what we have here. So we have to use the chain rule on these three terms. Not here. This is here with the negative x squared, we'll just use our normal procedures, and the same thing with the -4. So how does that work? So with y cubed, we're going to wind up with 3y squared using the power rule, dy dx. Then we have for y squared, we have 2y dy dx. Again, using the power rule to solve for the derivative of y squared. Then we have -5 dy dx. And that's because we're applying the power rule to -5y. Then we have -2x equals 0. So what is the actual value of dy dx? That's what we're after. Well, we're going to gather up the like terms. Which means the ones that have dx, dy dx in them. We'll set everything else to the right-hand side, and then we'll factor out the dy dx. Okay, great. So let's do that. And now I can just simply divide. And we're done. Wow. So yeah, it's getting a little bit involved here, but we can do it. Okay. It's not that much different from what we're used to. It's not like there's a bunch of new rules or anything. So anyway, all right, now here they want us to find the slope of the graph here at the point 3, 1. So in other words, it's an implicit differentiation problem. So let's work on that one for a bit. Oh man, we really have a mess on our hands this time. Okay, so they want us to take the derivative And so here's how it's going to go down. Okay. So now for the one on the left, we're going to need the chain rule in a couple of different ways. So we're going to apply the chain rule as follows. Oh, okay. Actually, I'm going to need more room for the right hand side. I'm going to need the product rule. Okay, but on the left hand side, just let me just quickly remind you, real fast, how the chain rule works. It's applied to composite functions. So for something like this, let me use a slightly different example here. If you had, let's say this was our what we were trying to differentiate in the first place. Okay, what would have been our procedure? Okay, so you would have had 2 times 3 times x squared plus 3x to the first power times the derivative of whatever's inside here, which is 2x plus 3. Okay, so you have 6x squared plus 3x times 2x plus 3. So here we have the 2 times the 3, x squared plus y squared to the first power. And then what you're seeing here, this is the derivative of what's inside these parentheses. But of course, the y squared has a derivative of 2y dy dx. That's why it works out that way. So on the right-hand side, let's take a look at that. And again, it's the product rule. So we're going to have the first term times the derivative of the second, plus the second term times the derivative of the first. Okay, so we're going to have to bring all this stuff together. So in other words, wow, look at this. So here's the original question. So when we differentiate both sides with respect to x, the left-hand side turned out to be this. And the right-hand side was this. So now we're going to try to simplify it as much as possible. All right, so on the left-hand side, wow. All right, so I guess we're going to have to do a lot of multiplying here. And so ultimately what we're trying to do is get all the dy's together on one side of the equation. All right, so for these two, multiply these out. All right, so what does that leave us with? So when we multiply these two terms together, we get 12y cubed dy dx. 12x squared y dy dx. 12 xy squared, 12x cubed. And then the right-hand side equals 100x dy dx plus y. Wait. No, sorry, x dy dx. Plus y. Oh my God. All right. So what we're basically going to try to do is start organizing this a little bit. Actually, we should probably write, it would probably be easier if we multiply this 100 by these terms. Let's take care of that right now. This is 100x dy dx plus 100y. So what I'd like to do is on the left-hand side have all the terms that do not involve dy dx. These go to the right. This one can get moved to the left. And then I have to subtract these two terms. And that is the 12y cubed. And then whatever was left over from before, 100x dy dx. Okay, so now we're getting somewhere. May not seem like it. And now we can just divide. I think they may have overdone it with this example. I mean, really, you're just still learning this. So throwing something this messy at you, maybe it's a little early for that, but you got it. I mean, you're starting to get the idea of how this works. And so I'm sure that we can do some consolidating of these terms, but I mean, they've got a simpler version than I do, but I'm sure that we could go through it and simplify it some more, but that's exactly what has to be done. So now this is interesting. I wasn't expecting this. Um, I've never heard that word before, lemniscate. It's like a big infinity symbol on its side. And I guess they wanted us to find the slope at that 0.31. And so you would have taken this derivative, you plug in 3 and 1, and you would have found that the answer is 13/9. Wow. All right. See, now this is good. This is a standard down-to-earth example of implicit differentiation. Let's take a look at this. All right. So we differentiate both sides with respect to x. But you notice the right-hand side is just going to be 0. Okay. So we're going to have 4x cubed plus 7. Now this one requires the product rule. And then this one is the chain rule. All right, so we'll multiply everything out. And then we can just add all or move all the terms that contain a dy dx to the right-hand side. And then we can factor that out. And then divide. All right. So which one is that? It looks like it's C. Beautiful. All right. And now here's another one. They want us to find an equation of the tangent line to the ellipse. And so we're going to use implicit differentiation, but then at the end, we're going to substitute for 1 and 7. Okay. All right, let's try this one. So again, we'll differentiate both sides with respect to y, x rather. All right. So we can split these up into individual terms. All right, so this one is going to be actually, I'll tell you what, let's do this. Let's move those constants outside just to keep it simple. And then we'll have 1/2 times 2x plus 1/98 2y dy dx equals 0. All right, let's rewrite this as and then we'll subtract that from both sides. And then we'll divide. And then we can rewrite this. Dividing by y over 49 is the same as multiplying by its inverse. So we'll end up with negative 49x over y. But they want us to solve for it when x is 1 and y is 7. All right. Oops. Okay, so that Okay. So in other words, the slope is -7, but the equation of the line is going to be okay. I missed that part. They want the full equation of the line. So um and so the point they're giving us is 1, 7. So yeah, the equation is y equals -7x plus 14. Beautiful. All right. So that's that. So that's our interlude into the area of implicit differentiation. You don't see it used very frequently because, like I said, it only shows up with equations that are so messy that you can't realistically rearrange it so that you have y on one side and all the x's on the other side. But when you do run into them, you do need to use this technique. Okay, so anyways, we're going to move on now to 6. All right, I believe this is the end of chapter 2, by the way. Let me go take a quick look. Yes. Okay. Now this is more like applications of differentiation. So now, of course, they love their physics examples. They've got this cone that it looks like it's filling up with liquid, and so the volume of a cone is uh, pi third 1/3 pi r squared h. Okay, so let's write that down somewhere. And they just want to remind us what they're referring to here. Here's your cone. Okay, now what they will want to know is how quickly is the water filling into the cone, basically. So when water, or how, in this case, how fast is it spilling out of the cone? Okay, so what they want you to do is differentiate this. So that what they want to do is assume that v is a function of time. And so they're going to need us to differentiate this implicitly with respect to time. So, all right, well, let's try that. Because you notice how time doesn't even appear in here. It's going on behind the scenes. So that means that dv dt now pi is a constant. Okay. Now, and again, if you notice, we're implicitly assuming that both r and h are functions of time. And okay, in other words, what they're basically saying is that if you notice, if the water level goes down, the radius of the remaining water is changing, and so is the height. They're not referring to the cone itself. They're referring to the amount of water that's left in it. So as it goes down, r is shrinking, as is h. They're both functions of time. So that's the whole point of this example. So that means that, you might say, well, these are constants, aren't they? Well, they are, but in this case, they're changing over time. So we have to take that into account. Now, here we need the product rule, by the way. Do the first term times the derivative of the second, and then the second term times the derivative of the first. So remember, so using the power rule, we have 2r, but then we need the chain rule so that it becomes r dt. And so, oh, they're not, that's it. That's all they wanted us to do. Okay. I guess they figure, I mean, we would need more information to come up with the actual values, but they just want us to see how we can connect the changes in both the radius and the height with respect to time and figure out how quickly the water is spilling out of the cone. All right, here we go. Let's try this one. No, no, this is interesting. They want us to treat y and x as both functions of t. Okay. So if that's the case, of course, that's not usually the way it works, but I mean, in this case, we're assuming that they're both functions of t, y equals x squared plus 3. Now, the 3 is a constant. Any way you look at it, it's just going to drop out. So, I mean, this is it. We're done. And here they're giving us some specific values. If we're assuming that x is 1, dx dt is 2, that means we can solve for dy dt, which is 4. All right, so a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. All right. So the rock goes in, and then you've got all of these circles rippling out. Oh, you've seen this before. It's kind of interesting to watch it. And what do they want us to do? The radius r is increasing at a constant rate of 1 foot per second. It's spreading out. So dr dt is 1. And in addition, when radius is 4 feet, what is the total area of the disturbed water changing? So the area is a pi r squared because it's a circle. Dr dt is, of course, 1. We just saw that. And, we want them to know dA dt. When r is 4. All right, so the first thing we have to do is differentiate this expression. Now, pi is a constant. We don't have to worry about that. So we're going to have 2r based on the power rule, but then we need to use the chain rule because r is assumed to be a function of t. Okay. And now, if you plug in 4 for r, well, oh, yes, that's right. We do know dr dt. Oh, beautiful. So dA dt is 8 pi per minute or second, however they defined it, foot per second. Okay. So it's 8 pi feet per second. Actually, it's square feet. Um, Interesting. Now here we've got a balloon that's getting bigger. So we're treating it as a sphere, of course. And the air is being pumped into the balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. So V is the volume. R is the radius. dV dt is 4.5 per minute, that is. Okay. So what do they want to know? Oh, find dr/dt. All right, great. So they're reminding us here that the volume of a sphere is 4/3 pi r cubed. So we're going to differentiate this with respect to t. And notice again, t is not actually shown here separately. This is implicit differentiation. So we apply the power rule to r cubed, and then we need the chain rule. All right. Now we were told that we want to know dr/dt. We're solving for dr/dt when r is 2 feet. Okay. Whoops. Find dr/dt when r is 2 feet. Okay. All right. Well, fortunately, we do know that dv/dt is 4.5. R is 2. And then we can use all that to solve for r/dt. So this is 12. And that means we have 4.5 equals 48 thirds pi, which of course is just 16. So yeah, they're expressing 4.5 as 9/2. Let's try that. 9/2 over 16 pi. Oh, what? Well, all right. So that means I think the reason why they're doing that is so that we can simplify it to this. Okay. 0.09. Okay. All right. So what do we have here? A point is moving along the graph of the function y equals sine 6x. Such that dx dt is 2. Find dy dt when x equals pi over 7. All right, so again, they didn't actually say this, but we're assuming that x and t, y and t rather, are both functions of t. Now, if you remember, the derivative of the sine is the cosine, but since this is 6x, the chain rule tells us that this is going to be cosine 6x times 6, but then we also need dx dt. So so you can plug in, oh, we have two numbers to plug in. We know that x is pi over 7. And dx dt is 2. So first we have to go look up the cosine of pi over 7. Or actually, maybe this is good enough. We could actually figure out the exact value, but I think this is what they wanted. So 12 cosine pi over 7 Oh, no, wait a minute. No, that can't be right. Um, okay. Oh, I know what I did wrong. Okay, sorry. I lost one of the sixes right here. All right, sorry. This should have been 6x. No wonder. Okay. Ugh. After all that, I just copied it wrong. So yeah, now we're good. Okay. Okay. 12 cosine 6 pi over 7, and that makes it b. Okay, great. Oh, what's going on here? Uh, the volume of a sphere, which we just saw a few minutes ago, is 4/3 pi r cubed. And the radius is increasing rate of 6 inches per minute. So dr dt is 6. And we want to know dv dt when r equals 11. All right. So that's implicit differentiation. Now we just plug in some numbers. So we can simplify it a little bit. 4/3 times 3 is, of course, 4. And we know that dr dt is 6. We know that r is 11. And that's going to be 2904 pi. There it is, C. Beautiful. All right. So that kind of wraps up this discussion about rates of change. So they basically wanted to show you some physics applications of the implicit differentiation that we learned in the earlier part of the previous chapter. So that's kind of it for now for differentiation. Now, of course, differentiation will show up everywhere in this course and in Calc 2. So we're never completely through with it. But at the moment, there won't be any new rules until I think they're going to next introduce trig derivatives. So let's take a look at where we're going with chapter 3. Here we go. Oh, okay. No, it's not what I was expecting. All right. So now they're getting into some very important territory here. It's an area of math called optimization. And so what they're trying to do is basically take a function and find any points where it reaches possibly a maximum value or a minimum value. And so they're going to show us how to do this with derivatives. Okay. So let me just sketch out a quick example of this. Imagine the following situation. Suppose that you're running a business, and let's say this is your profit function. Here's your profit. Profit is your dependent variable, and the units of the product that you're producing are the independent variable. And let's say the function is it's a parabola, basically. Well, just by looking at this graph, it should be pretty obvious that this point right here is where you want to be, because this is where your profits reach their maximum possible value. So let's say that if we produce 100 units of this good, our profit will reach its maximum value of $1,000. Anywhere else, like if we only make 99 units or 101 units, we could be doing better. So the question is, how do we find this point without sitting down and recalculating every single possibility? We're going to take this function and we're going to use derivatives to figure out where this point occurs. Now, you could also imagine something like this happening. Let's say here you're looking at your cost of production, and here's the number of units you're producing. The function looks something like this. Then clearly this is where you want to be because this is where your costs are minimized. So up here you have your maximum profits. And here you have your minimum costs. So the question is, how do we find these points? That's what this chapter is, or this, yes, this chapter is all about. Taking functions and finding points at which they might reach a maximum value or a minimum value. Now, not all functions have a minimum or a maximum value, and we need to figure that out too. In other words, we need to be able to look at a function and determine if it has a maximum or if it has a minimum, and if it does, where is it? But as it turns out, all of this is based on what we just got through doing. Pretty much it requires us to know the first and the second derivative of this function. Okay, so we'll see how that goes. This is a very complicated area to study. So, but I think we're ready for it because and by the way, there's no more implicit differentiation here. It's just straight ahead differentiation with the rules that we know and love. And the functions that we'll be looking at will probably be relatively straightforward. So now, first of all, in terms of terminology, I just want to mention a few things here. A function can have a maximum or a minimum. Now, here's where it gets a little interesting. An extremum is either a maximum or a minimum. In other words, the words extremum means it could be either a maximum or a minimum. And also, here's where we want to be careful too. The plural of maximum is maxima. The plural of minimum is minima. So you can probably guess where this is going. The plural of extremum must be extrema. And that's, of course, because these are Latin words. Most math words, most terms in math, many of them, I shouldn't say most, a very large number of them either came from Latin or Greek. It depends on who invented this first. And, there's others too. Sometimes there's French and there's German, but a heavy percentage of these terms that we are learning are based on either Latin or Greek. Especially the Greeks invented a lot of what we know as geometry. So a lot of terms in geometry are Greek words. The Romans, during the Roman Empire, a lot of math was developed in the area of algebra. And so a lot of these terms are Latin words. So how do we find them? Okay, now let's see where we're going with this. We don't have time to get too deeply into this right now, but here, let's look at these graphs real fast. So on the left, we have a parabola, and clearly it has a minimum. Now, if you notice, the result that we will get will depend on the interval over which we're defining our function. So if you notice on the left, that parabola is only being considered over the interval from -1 to 2. Okay, so because of that, you can see from the graph that it reaches its minimum point when x equals 0, reaches its maximum point when x equals 2. If we define this over a different interval, the minimum wouldn't have changed, but the maximum would have changed. So the one on the left, if you notice, is closed. It's defined with the square brackets, meaning it includes both -1 and +2. On the right, that's not the case. It's an open interval, which means it doesn't include either -1 or +2. So that changes the results. And we're going to see how that works when we get more deeply into chapter 3. Okay, so we're going to learn the techniques for identifying where to find the function's maximum, where to find its minimum, or finding out that it doesn't have a minimum or a maximum in the first place, which is possible. Okay, and so we're going to, as I was saying before, we're going to use derivatives to do this. So that's where we're heading. I don't want to, I think it might be a good idea to start this from scratch in our next session, not right now, when we've been working so hard on our implicit differentiation. We want to start this fresh with a new section, which we'll do the next time we meet. So anyway, so I'll see you then.